Welcome. In this video I'm going to talk about my small box, which is a voltage logger. It's a very high resolution measurement device. With the current setup I'm using it with 4 inputs. So there are 4 channels, red is the plus, black is the minus, and there is just one USB connection and a few LED lights just to show the status of the machine or the device. So I'm going to open this box and show you what's inside. So now we are inside the box. So here you can see the 4 banana contacts, plus up here and minus down here. They are just connected by simple wires to the first circuit, and then this circuit is connected to the Arduino, and then we connect this Arduino, it's a Uno, to the computer. So let's talk about this device a little bit. This is a 8-channel and 24-bit resolution AD converter. It's an ADS1256 chip. So basically we have 8 channels here, 8 single-ended channels or 4 differential channels. I'm using this device in differential mode because there is less noise, and therefore the accuracy of the measurement is much more precise. So we have this input here, and then here's the main chip, the oscillator, and then these are the most important connections. Basically we have like 6 wires which go to the Arduino, and then the Arduino controls this circuit, sends the start signal, receives the data, and then makes it possible to read the data through the serial port. So you can program your Arduino with some code and just read the very precise voltage through one of those inputs. So the focus of this video will be on the operation of this ADS1256 because there are not so many resources on this board. However, you can easily buy this circuit for 15 to 25 US dollars. So it's not so expensive, and you can use it for a lot of things because 24 bits is a huge resolution, and in principle you can have 30,000 samples per second. So it's a quick device, reasonably fast, and it has a huge resolution. So there are many fields where you can use this device, and you can measure a lot of things, which is very good, I think. And yeah, so I'm going to show you the code for the Arduino, and I'm going to show you some measurements. I quickly want to go through the most important details of this AD converter. So we are talking about this ADS1256 board. So it has 8 channels. These are the single-ended channels, and it is also important that the resolution is 24 bits. So this 8 channel can be used as for differential channel, which essentially means that if you have the 8 channels, let me draw it. So you have 1, 2, 3, 4, 5, 6, 7, 8, and then you have, this is the plus, and then you have the minus for each channels. So if you use it in 8 channel configuration, then you are using each channel with its corresponding plus and minus connection. So therefore you have 8 channels. But then there is a high risk that you pick up a lot of noise through the minus wire and the plus, or either the plus wire, but you pick up a lot of noise with the wires, and then that is not cancelled out. So if you have poor wiring or poor shielding, then you will end up with a lot of noise, which can hinder the accuracy. And since we are talking about the 24-bit AD converter, it's very sensitive. So you can differentiate between very small changes in the voltage. And if you want to actually do that, you will need to have a very precise signal. So therefore you can turn this into 4 channels. Basically you keep the positive part, or the positive inputs of the board like this, but then you are using the positive inputs only. So therefore you group your positive inputs into channels like this, and then this becomes 1, let's make it 1 prime, 2 prime, 3 prime, 4 prime. So you will have your 4 channel. But in this case, due to the differential setup, you will be able to measure more precise signals, because you can cancel out the noise more or less. But now I don't want to go into details how and why the differential inputs work, but I just want to tell you that if you need very precise signal measurements, for example, you want to hook up your device with a thermocouple, or you just want to measure very precise voltages from something which has very low signal level, you should use the differential inputs and not the single-ended inputs. So this is the best solution for precise measurements. So we have 8 or 4 channels and 24 bits, and the maximum data rate is 30,000 samples per second, and I believe that this is per channel, but there is an option that you can cycle through the channels very quickly, so maybe you can do it for 8 or 4 channels, but my code is only valid for 1 channel. And then you can use it with SPI, which makes it very simple to use, less cables and stuff. It operates at 5 volts, and then it has a built-in PGA, so actually you can choose the input voltages or the region for the voltages, and you can buy this AD converter as a board, and that's what I'm going to introduce here. So it's very simple to use, because you just have another circuit, you just connect it to your Arduino, you install the corresponding code, on your Arduino system, and you just use it. But to show you how precise is this thing is, I want to just tell you some very basics which you might know. But 24 bits is essentially, I'm just using rounded numbers, but this is like 16.7 million different levels basically. So if you set your PGA to 1, so you don't use any division between your reference voltage and the input voltage basically, then that means that if your reference voltage is 5 volts, then this device, if you use the differential inputs, it will measure between plus or minus 5 volts, which means that you cover 10 volts region. Just to so this is 10, right? So now just to see how fine is this resolution is, just let's divide this 10 watts with 16.7 million. So essentially you get something like 5.96 times 10 to the minus 7 volts, which is 596 nanovolts. So if you receive, let's say, the difference between 2 bits, so if you receive the bit, let's say 200, and you receive 201, then this difference is just 596 nanovolts. So it's a very small voltage difference. So therefore you are able to use it for very sensitive devices, but then you have to have a very nicely shielded system which doesn't act as an antenna and picks up all the signals in the air. And then just to talk about the sampling rate, so we have 30,000 samples per second, which means that one sample will take 33.33 microseconds. So basically the time between 2 samples is this much. And then if I understood correctly, this is only just per channel. So if you have, for example, if you have to go and cycle through 8 channels, then of course you just multiply this number by 8. So you have, if you read the 8 channels after each other, like switching on one channel, reading it, switching to the second channel, reading it, then you have like 266.7 microseconds. So this is the time for reading all the 8 channels. And then if you have 4 channels, then of course you have the half of this thing, microseconds. So then this corresponds to like 3750 Hertz sampling rate for 8 channels total. And yeah, if you read half of those channels, then it will be the doubles of the initial speed, so 7500 Hertz. So it's a quite quick device. But for like regular things, if you want to use it as a multimeter, or if you want to track the change of the temperature, then you don't need this high speed. You are fine with 10 Hertz or maybe even less. So you just need a few samples per second, because if you use it as a multimeter, you just want to read it with your eyes. So maybe if it is changing too quickly, you are not able to follow the changes. So this is just the basics. I will go and open the Arduino code now, and for real, and show you how my code is built up. There are a lot of comments and a lot of unused lines, but I go through the code briefly, so you will see how it works. Actually, I did not write the entire code, especially the libraries. So I took the libraries from the internet. I put the link in the description, so if you want to build your own code, or you want to understand the principles of the code, you should follow the link. It's a GitHub link, so you just go there and download the code, and yeah, just tailor it to your own needs. But basically, here we are just using the SPI library and the library which I have downloaded, and then after that we just assign some pins for the different pins on the ADS1256. So we need a start pin, a clock pin, a data ready pin, and a reset pin. But I'm not using that, because sometimes if I use the reset pin, it works funnily. So I just skipped that pin, so it's commented. And then I introduce another variable called sampling freak. So, but I will tell you later what it means. So I initialize the ADS, and then we go to the setup menu. So this is the code which runs only once when you boot up your Arduino. So we should start with a high baud rate, because we need high speed. So I use this, and then we start the serial. So we start up the board, the AD converter board. We reset it, so we set everything to default, and then we wait a little bit, and then we can have our own pre-configuration. So I will show you the datasheet and tell you some details about it later, but basically you just set up the different registers of this machine or device. So you select the inputs, you select the data rate, you do a self-calibration and things like that. And I just made a comment here that if you are using very high samples per second, your channels will behave funny. So I would not recommend to use very high, like the highest settings, because I'm not using the device properly maybe. So I just noticed that I'm receiving very funny numbers. So now we have our loop code, so this runs over and over again until you remove the power. So first I want to start a timer, because I want to keep and follow the time between each readings, because I want to read the voltage continuously. So basically we start our timer, and then we go to the serial port, and we are waiting for a character to read. So in my code I have written a software for this on for the PC. We are controlling this Arduino with characters. So if I press a character and send it through the serial port, then the Arduino will answer with something. I will show you here. So we have one like character input, and then these are not important now, and we have another character input because sometimes we need to tell two things to the device. So basically I have a switch case system here. So if I receive, or no, if the Arduino receives some characters, it will do something. So for example, if I send the R character to the device, then it will wait for another character, which is basically a number, and then it will do something. What it does here is if we have R, that means read, so we are reading the register. So what we do here is we receive the R, and then we tell the number of the register, like 1, 2, 3, 4, whatever, and then the Arduino will send us back the value of the register. This is very useful because we want to know, for example, what is the data rate, or what is the which input is on now, so which input we are reading at this moment, and so on and so on. So we do that here. Yeah, this should not be commented. So this is the proper code. So it receives the character R, then it will wait for another character, which is a number, and then according to this number we will get the value of that register, and we print it on the serial port. And then we do the other way around, so we can write those registers, but this is a bit more complex. I mean, just one extra step. So basically what we do, we send the W to the Arduino, then it will wait for another number, which is the number of the register, and then it will wait for another number, which is basically the value of the register. So we tell the device that, alright, write this register, the CIN1, and put the following value to this. And then I put a comment here. So for example, if I send W space 3 space 128, that means that we are writing the third or number 3 register, and we want to write the 128 value to it. And then these commented values were just for debugging, so I wanted to make sure that I really have those values in the register. So then we can go for the more entertaining parts. So for example, if I send capital R, then the system will calibrate itself, so it will do a calibration and an offset setup, and then we wait just a little bit to have the device settle down, and then we just get one conversion value. And yeah, of course we also select one input, which in my case is the first channel, or channel 0, but yeah, the first 2 pins on the positive side, because I'm using it as a differential stuff. We can also send just, for example, C. For me, C, because it's calibration, and then we just make the device to calibrate itself, and that's all. Sometimes it can be funny to do something like this, and it's important to calibrate sometimes, because sometimes the calibration changes itself. I don't know why, but sometimes it behaves funny, so we just do this. And then we can do, I think this is one of the most important thing which you might be interested in. So we can have the single channel reading continuously. So we send a letter S and another number, so I'm just writing this. Let's put it in quotation marks. So we send the S, and then the code will wait for a number, integer. So for example, we send something through the serial like S space 300, and the unit of the 300 is milliseconds in this case. So then it will know that the delay will be 300 milliseconds, and then we do a self-calibration just to make sure that the offset and everything is good. We wait a little bit, and then we set up the data rate, so basically the sampling frequency, and then we make a while loop. So while we don't stop it with by sending a capital N through the serial port, this loop, which I select here, will run continuously. So we have the elapsed time. If you remember, we started the timer when we started the loop. So then we have our current time by checking the millis just right now, and then we subtract that value from the we subtract the start time from this, so we get the elapsed time, and then we write that on the serial port. We make a tabulation, and then we switch on the first single-ended input, so basically the pin number 1 or 0, pin number 0, but that's the first pin, and then the negative pin next to it, and then we get the conversion value. And then we make a tabulation just to separate the characters, because you want to read it with something, and if you have like these standardized separation characters, you can easily plot your values or put it in Excel or something. You can make the processing easier. So we make some space, we wait microseconds, just 100 microseconds, not milliseconds, and then we switch to the next channel, and then we get the conversion value, and then separate, and so on and so on. So we read all the 8 channels like this. So the full out, I cannot write, so the full output looks like this. So you have the time on the first in the first column, and then there is a space or tab, and then you have the value for the channel 1, channel 2, channel 3, and so on and so on. And then after you write or print the line break, we wait for 300 milliseconds. So what we did here. And of course this time is not precise, because we do a lot of delays here, microseconds. This is like 800, so we already have almost 1 milliseconds. And then to switch between the registers or the pins and get the conversion values, that also takes time. But this time is like 1, 2 or 3% error as compared to the sampling frequency if you have like several hundreds of milliseconds, so it's negligible. You will have like a very small shift in your sampling frequency, but it's not a big deal. You can write another timing sequence here, and then you can subtract the time which was necessary to run your code, but in my case I don't really care if it's like 500 milliseconds or 508 milliseconds, the difference between 2 signals, because I'm not measuring the frequency or something. I just want to know the the voltage values for a given period of time, so I don't really care. And then there is another method which is basically the same as the previous case, but in this case we use the differential inputs, so we connect two positive inputs, but basically the same. We send the D character to the Arduino, and then we will read an integer number, for example 300, 500 something, and then we set up the data rate or sampling rate of the Arduino itself. We do a self-calibration, we wait a little bit, and then we do the same. So we have a while here. So until we don't receive capital N on the Arduino device, we just run through this code over and over again. So we start the time, we print the time on the first in the first column, and then we can have some delay if it's necessary, but I have noticed that sometimes it's not really necessary. So in this case I commented out. But if you experience some weird stuff with your code or with your numbers, then you should add some let's say few dozens of microseconds delay. And then you switch on the first input, the positive and the first positive and the second positive pin, and here second positive and third positive and fourth positive, and so on and so on. So you just switch input, read the value of the input, make a tabulation, switch input, read the value, tab, and so on and so on. And then we wait just for a little bit. And then if you want to make something else, you can add more cases here, and also you can have some default. So if you want your device to do something, if you don't send anything in your switch case, then you can put it here. So this was the code. So now I'm going to show you some measurements. So I hooked up this device with a power supply, and there is a multimeter there to show you the voltage, and there is a potentiometer, so I can change the voltage coming from the power supply. So the power supply comes here, goes into the potentiometer, comes out, and then this goes to the device, to the box, and then I have the two connections for the multimeter. So let's first check what is our power supply voltage. So I just it's 3 volts. And then what comes out from the other side of the potentiometer is 969.6 millivolts. So let's make a reading, just a simple or single reading by sending a capital R. So we get 1.00 something volts. So that's not so bad. And then let's change the potentiometer. So I just do some random twist. Let's measure it again with the multimeter. So seems like I managed to put it on 0. So let's turn it in the other direction. 1.683. So do another reading. 1.683. 78. So there is a difference of 100 millivolts or 0.1 volt. Maybe that's a lot, but now let's do something like doing a continuous measurement. So let's send the space and then just put it, so we get the value at every 1 second. So you see the first column is the time in milliseconds, and then the second column is the voltage, and then the other columns are just basically the other channels. So now we have, and then if I change the voltage, yeah, so you can see that the voltage is not so different. So we are reading like 2.53 on the multimeter and 2.47 is read by the computer or the analog digital converter. So it's pretty much close, I would say. It's a reasonable time difference. It's a reasonable voltage difference. But we never know if we can trust the multimeter. So I don't know if it is the multimeter or the ADS1256. So yeah. But let's just not stop there. So I want to show you my own software as well. So I made a software which will draw you a chart. You can choose your channels, you can see the time, you can do some communication with the Arduino, and you can save everything into file. You can change the sampling interval. I will make it to 300 milliseconds, so you will see the changes quite often. You can choose between the different PGA settings. You can stop the measurement after a certain time, and you can have a time window, which means basically that you will start to shift your X. So you will delete always some values from the beginning of your measurement or shift out from this window. So you will always see the most recent results. So if you make this time window to a very small window, actually you can use this software as an oscilloscope, or sort of. So I turn on the first channel, I connect to my Arduino. I know that it's connected through the COM9 port, and then I just simply start. So now there is no reading because I haven't connected the power supply, but now I turn on the power supply. So we have 2.47 volts, and now I start to turn the potentiometer in some direction. So now you see I'm at the end of the potentiometer, so we reached the power supply's voltage, and now I start to turn it down slowly. So now you see the decrease. Now you see that we are slowly reaching the ground. So we are at 0. So you see it can be used. And now I show you that if I stop this and let's change this to 100 and start it again. So now we have more frequent signals. So now you can see that I'm just turning the potentiometer up and down, up and down. And of course you can change this to even smaller values, like 1 microseconds, or sorry, 1 milliseconds, and just start it. Then it's like almost continuous. Or you can go and change this to even smaller values, but at this moment I haven't changed it to smaller values because I usually log my voltages at every 1 or every 5th second. So For me this is enough, but you can see that now I'm just rotating the potentiometer up and down, and yeah, you can see that it follows the changes quite nicely. And it's quite stable. So yeah, if you do some programming like this, you can turn your very cheap device into a very serious device. So I think I will finish the video here because it's already very long. I hope you enjoyed it and it was useful for you. If you need any help with the Arduino code or whatever, just let me know in the comments, and see you in the next video.